Okay, thank you for the invitation. So today we are going to talk about uncertified DAG-based consensus protocols. We will explore the recent development in this field. Let me just start with this outline. So we will discuss three protocols that I also mentioned as abstract: Cordial Miners, Mysticeti, Starfish. There were more than these three before, like Hashgraph and some others, but we'll focus mostly on this because they allow to decrease the latency quite significantly. Also, if you want to have an overview of this talk with reference to papers, you can also use this QR code. Good. Let's start with the system model. So we consider as a standard model. So we have 3 f+1 nodes in the network, out of which at most f are Byzantine. So that means that at least 2 f+1 nodes strictly follow the protocol. And f Byzantine nodes can deviate from the protocol arbitrarily. And we focus on so-called partially synchronous models, so which is kind of like in between asynchronous and synchronous models. It means that there is some unknown moment called global stabilization time, until which the communication between nodes is asynchronous. It's kind of like unpredicted in which order the messages arrive and when. And after this moment, communication gets synchronous with more control delay delta, and this delta is part of the protocol parameter. This constant is known to nodes. And we want our protocol that will just build consensus protocol to be safe during asynchrony periods, and we want it to be live and make some progress when we have synchrony. So our goal is to build a Byzantine atomic broadcast using special quorum-based acyclic graph. So in this model, we just have nodes, and these nodes are connected to clients, and clients submit transactions continuously to them. The goal of nodes is just to create blocks whenever it's possible and to include in the blocks some subset of transactions. Each block includes also references or hash pointers to prior blocks. Thereby, if you just look at all the blocks, they form a directed acyclic graph. Why it's called quorum-based is just because if we look at every individual block, then if it's a block of round R, then it has to reference a quorum of blocks, a quorum of 2 f+1 blocks from the previous round. Like these conditions allows us to not advance too fast, just to not be beyond the network, just to progress the DAG construction in cordial way. And the second condition, so for which we require from the DAG, is that each honest node creates at most one block in one round. The goal is to build the protocol such that when each node reads its own local DAG that it has at the moment, it tries to find a sequence of blocks, and it can extract transactions also from the blocks, but the goal is just to find a sequence of blocks such that it satisfies these two properties. The sequence is growing after global stabilization time, and it means that every block of honest node will be included in the sequence, and it satisfies the safety property. It means that if you have two honest nodes and they have two different sequences, then they should be consistent, meaning that one should be a prefix of another. So it means that when the nodes will say execute the transactions from the blocks, they will come to the same state, ledger state. And let's start with just how it looks like. So I will draw such pictures at almost every slide. So we have here 4 nodes, A, B, C, and D. And our DAG grows from left to right. So round 1, round 2, round 3, etc. And as I said, it's a quorum-based DAG, meaning that every block, if you look at every block, then it has at least quorum of references from the previous round. So quorum here it's 3, because in total we have 3 times 1 plus 1, 4 nodes. Quorum is 3. What we can see here, so it's possible that for some rounds there are no blocks, but for some rounds some node has 2 blocks. These blocks are called equivocating blocks. And this is exactly why it's called uncertified. So in uncertified DAG, if you create your block, then you immediately send it to all other nodes. And upon reception, you as a node, you just receive a new block and you just check, only check that you have all the causal history of this block. If you know all the causal history, then you can immediately integrate this block to your local DAG and optimistically add it and build your block on top of the received one. And because of this design, equivocations are possible here, like here D3 and D3 prime are equivocating blocks from node D. And for instance, D creates D3 and sends this block to node A, and D also created block D3 prime and sent it to node C. And since A and C created their blocks on top of these equivocating blocks, both blocks will just stay in this data structure. And this is very different from so-called certified DAGs, where every block can be associated with a certain certificate. In certified DAGs, basically, you also create a new block, and then you send this block also to all other nodes. But then you don't immediately integrate this block in your local DAG, even if you know the whole causal history. You first need to check whether it equipped with a certificate. So you reply to this block, to the block creator with your signature saying, confirming that, okay, it's your first block that I have seen from you from this round. And the block creator receives signatures, aggregates signatures, and send this aggregated signature or certificate to all other nodes. And only upon reception such a certificate, you can integrate this block to your local DAG. And just because there are certificate and certified DAGs, you can avoid all these equivocations because of the quorum intersections. And it's not possible just to create 2 certificates for 2 equivocating blocks. But uncertified DAGs, they progress, they are built a little bit faster than certified DAGs, but there are some nuances, like there could be equivocations and some blocks could be not well disseminated before they appear in the local DAG. Okay, let's move on to the design in decision and some sequencing rules of Cordial Miners. So what was suggested in this protocol is they suggested some efficient rule how to find this sequence of blocks. The idea is approximately as follows. So we want to agree which blocks will serve as anchors when we'll slice the DAG. So we'll have some here we have a notion of waves. So each wave is just 3 consecutive rounds, round 1, round 2, round 3. It's wave number 1. And the next wave also consists of 3 rounds, round 4, round 5, round 6. And in the first round of each wave, we assign one leader, one node that is seen as a leader in this wave. So here it's node B will be the leader, here node C will be the leader, and we can use any deterministic orders or any round robin method is fine here. And then it's not sufficient just to say, okay, this is our leader nodes and they'll be as anchors, but because we could have equivocations, so you could receive one leader block from this guy and another guy could receive another one. And then when we'll try to slice the DAG, we'll come to different pictures and we'll come to inconsistent sequences. That's why we need to ensure that only one leader block can be kind of like committed by all the network. And for this reason, we try to mimic the notion of certificates that we had explicitly in certified DAGs, and here we do it like more implicitly using the DAG structure. So here, the blue blocks here in round 2, they are votes. So a block is a vote for the leader block if it's a block from the next round and it's linked to the leader block. And in addition, the second condition here is that if you look from the perspective of this block, for instance, from this block, if you look at the perspective from this block, the whole causal history of this block, then you can see that, okay, in this causal history of this block, node B did not equivocate. So it was an honest node in the perception of node C from this block. So, but the main condition is definitely that the block should be linked. That's why the block from node D in round 2 is not a vote for this leader. And these votes are similar to explicit signatures that exist in certified DAGs. In round 3, we then look at so-called certificates. And certificate is just a block in round +2 from the leader block, such that it can observe a quorum of blocks voting for the leader. So it's just such an implicit notion of certificate. And one important observation about these votes and certificates is that if there are two equivocating blocks from, say, this guy B in round 1, then both of them cannot have two certificates. Just again, because of the quorum intersection. So because each certificate requires a quorum of votes, and since honest nodes don't equivocate, they vote consistently and they vote only once for the leader. It's not possible to create two certificates on the DAG under the assumption that we have. And there are a few rules how we are going to commit. So one is a direct commit rule. So here, for instance, block C4 is directly committed just because there is a quorum of certificate for this leader. So B1 is not directly committed because there is only one certificate for block B1. All other blocks, if you just check, then they don't satisfy the condition that they observe a quorum of block voting for B1. That's why B1 is not directly committed, but C4 is directly committed because there is a quorum of certificates for this block. Indirect commit is a little bit more complicated, but it basically means the following. So if we have a directly committed leader block, then we try to find whether this block goes through the certificate of the previous leader block. And this is the case here. So C4 is linked to the certificate. That's why B1 will be indirectly committed leader block. And I just changed a little bit the DAG here. And in this particular scenario, B1 will not be indirectly committed because there is no even a certificate for B1. That's why C4 cannot be linked to any certificate for this block B1. So in this case, B1 is so-called skipped. And our goal is to find just a sequence of all directly and indirectly committed leader blocks. And these leader blocks will be used as anchors to slice the DAG. I just constructed one more round here, and let's assume that we find just a sequence of committed leader blocks. In this case, it's say B1, C4, and then D7. And what means slicing? It means that we want to traverse the DAG starting from the given committed leader block. So this is just the first round, so we don't have anything to traverse. But here, for instance, C4, we start traversing from C4, and we don't have a link to this block D from round 3. That's why when slicing the DAG, we can only get all these, say, red blocks. And we try to traverse everything that was not traversed before. And when we do the same for D7, we just get these orange blocks. And then once we have these slices, so this like purple, red, and orange slices, then we can order the blocks, whatever we want inside the slices. For instance, we can also sort it by rounds inside, or we can also sort transactions within this sub-DAG somehow. And this way you can find a sequence of blocks. And then you can also extract the sequence of transactions. Okay, this was a design of Cordial Miners. And one more thing that I want to mention. Since the DAG was constructed in like uncertified way, there was suggested such a rule. So let's look from the perspective of node A. It created a block in round 6. And now I'm just thinking, what should I send to node D? Okay, definitely I need to send my block, but at this moment, I don't know whether node D is aware of these blocks from round 5. Probably B is just cheating, just the adversary. Maybe B didn't send its block to the node D, and then I need to send also all the missing ancestors or all the missing causal history of this block to the potentially missing history of my block to the to my peer D. That's why all these green blocks should be sent to D. And if you just think in this way, then basically in this like rule, this cordial dissemination, you need to send, I mean, the say block complexity, communication complexity is quadratic just because the same block would be sent between almost every pair of nodes. So this is very expensive on one hand. On the other hand, it allows you to have this smooth, immediate integration of the received block to your local DAG. Let's move to the next protocol called Mysticeti.
May we stop for a second?
Yes, yes.
Could you please go back to certificates and quorum of certificates? So is it true that we always, so epoch is free rounds, and we always have blue on second rounds and green on third round?
Yes.
Okay.
Yes. Yeah, we always just do in this way. So our wave, yeah, just a notion in this uncertified literature and certified as well. So the second round is always should have blocks that vote for the leader, and the third round is about certificates. We try to find certificates in the third round. Of course, you can generalize this concept and just say our wave consists of 5 rounds, and the first round is like where we expect the leader block. The second, third, and fourth is where we expect votes. But then the vote should be a little bit different definition. And in the last round, we expect certificates. It's possible to generalize in this way. Yeah, but here it's kind of like sufficient just to consider 3 rounds in a wave.
Yeah, thank you for the clarification.
Let's go to the next protocol. So the first one was not implemented explicitly as it was proposed, and the second protocol was like designed by Myston Labs, and it's already part of Sui blockchain, IOTA blockchain. So let me explain how it works. So the idea is pretty standard for BFT protocols, leader-based protocols. So let's look from the perspective of the block from guy C in round 1. So it proposes its block here, but when it's going to be sequenced. So we first need to wait until C will be directly or indirectly referenced by the leader block. And it will happen only in round 4, just because C is a bit unlucky. It could not be referenced by B because all the reference should go to the blocks from the prior rounds. That's why C can be referenced indirectly or linked with the leader block only in round 4. And then we also need to wait 2 more rounds when the leader block will be committed. And it means that the transactions in this block will be sequenced only like in, you can see in 5 rounds. And the idea of Mysticeti is just to design some rules such that we can improve the latency of blocks. So the first idea is just to implement pipelines. So previously waves, or you called it epochs, were disjoint. Now we want to have pipelines. So the first wave, it has intersection with the second wave, etc., etc. So we have intersecting waves here. And we have leaders already much more frequently. And next, what was also suggested, why not do that every block is a leader block? So, and they suggest, okay, you can use multiple leaders in every round, and hopefully it could improve the latency. This is just, I can say, that this is not necessarily true, especially in Byzantine environment. Just having multiple leaders in every rounds, it's a bad idea. But in optimistic case, when every node is honest and well connected, then it probably could be a good idea. But even that, it's a little bit hard to see from experiments. But anyway, the idea is just to have leaders more frequently, such that we can sequence a given block much faster. And the commit rules are pretty much similar, but of course here just it's a little bit more complicated, but we need to look again. For instance, if you look at some leader block, we first need to check, okay, is it directly committed? And this is decided at the end of the wave of this leader block. So for instance, block B1, we should check certificates in round 3, whether there is a quorum of certificates. They also suggested to have direct skip rule. In the direct skip rule, we just don't have enough votes in the voting round. For instance, let's look at this block A4, and there is only one vote in round 5, and it means that, and we have all other blocks in this round, it means that it's not possible to have a quorum of votes, and it's not possible to just have a certificate for this block. That means that this leader should not be used as an anchor when we will do slicing. There are also some indirect rules, and in indirect rules we should just extend the ideas of Cordial Miners, but here it's a little bit again complicated because we have multiple leaders. And what we need to do, we need, for instance, if some block is kind of like we cannot directly commit it and we cannot skip it, we need to rely on indirect commit or skip rule. And we need to look what happens in 3+ rounds, say round 4, and find the first committed leader in the right part of the DAG. We find the first committed leader, and then we need to check whether it's connected again to certificate. And if it's the case, then okay, then we can indirectly commit that leader that is connected through the certificate to the committed leader in future rounds, in 3+ rounds. That's basically the rule. There is also indirect skip, and it's different from indirect commit that the next committed leader is not connected to certificate. Yeah, and again, one can prove that under assumption that at least two F+1 nodes behave honestly, we can prove that they will come to the consistent skip or commit sequence of leader blocks, and they will slice the DAG consistently. And let me give you just some example. For instance, here B1 is skipped because there is only one vote. A4 is skipped because again there is only one vote. But C1, C2, and all these blocks, they are directly committed because you can find a quorum of certificates. But what about, say, D2? So if you look at the D2, then there are, of course, these 3 votes, but you can find that there is no certificate for D2. There is no certificate so far for D2. That's why we cannot at this moment decide whether D2 should be committed or not. So we need to take a look what happens in 3+ rounds. Yeah, it means that we need to understand what happens in round 5 before deciding D2. Yeah, and I just extend by one more layer here, and we can see that B5 in round 5 is the first next committed leader. And what we try to do, we try to find a certificate that is linked to B5, a certificate for D2. And there is no certificate, and that's why D2 will be skipped. And then for D3, one of the leader in round 3, we also just have enough votes, but we don't have certificates, or we have not enough certificates, and we need to wait until what happens in round 6. So that's the way how it works. So we first try to decide through the direct rule, and then if it's not possible, then we rely on the indirect rule, such that some decisions that we make in future rounds will propagate the decisions for the past rounds. So in this case, D2 is indirectly skipped, D3 is pending. So, and that means that our sequence of committed leaders will be in this case. So we should go over all leaders that we have in the schedule, B1, C1, C2, D2, A3, D3. And we need to check which ones are skipped. If we skipped, then they will not be in the sequence of committed leaders. And in this case, we will have a sequence like C1, C2, A3, and D3 is still like in the pending state. We are not sure about the status of D3. And even though we already decided A4 and B4, we cannot continue this sequence of committed leaders because D3 is still like pending, is undecided. And then we use this sequence of committed leaders to slice the DAG into sub-DAGs and order the blocks in the causal path of committed leaders. And in this case, when we start just do this slicing, we'll get this following sequence of blocks. So first C1, it was the first committed leader. Then we start with C2, we traverse and we get A1, we traverse, we get D1, and we get C2. So C1, A1, D1, C2. Okay, and here just the typo. And then we traverse starting from A3 and we get A2, B2, and yeah, and also A3. That's it should be not D1 but B1 here. That's because when traverse from A3, the most far block that we can traverse and which was not traversed so far is B1. So it should be C1, A1, D1, C2, B1, A2, B2, A3. Good. That's the way how we find the sequence of blocks eventually. So we try to find which leader blocks are committed such that we have a decided status of all leader blocks before, and then we slice the DAG. But when implementing Mysticeti, the problem with Cordial Miners was that we had high block, say, complexity. So it's quadratic complexity, and it will slow down everything significantly if if there are some meaningful number of transactions in the blocks. And the broadcast rule in Mysticeti is pure pull strategy. What it means? If I am a guy A, then what I do, I just broadcast or stream only my own blocks to all other peers. I don't care how disseminated were previous blocks. And if another guy, say D, received my block, then it will request all missing ancestors, all missing parents, all missing references, and step by step it will fetch all missing history of my block. In good scenarios, in like optimistic scenarios, it lead to very good like latency and low communication complexity. But when there are some network disruption or something like that, then it could lead to some problems, including like high latency. And the motivation for the latest protocol that we are going to discuss today is communication and prior works. So basically, in Mysticeti, they use this so-called pool-based strategy, where you need to slowly pull unknown parents step by step. But as for Cordial Miners, the bad thing is that it has quadratic block complexity, communication complexity, and even for Mysticeti, you can design some scenarios more like theoretical, where it has also quadratic amortized communication complexity. So that means that to sequence 1 byte of transactions, all validators, all network has to spend a quadratic in the number of nodes bytes to exchange, just to sequence 1 byte of transactions. And the problem with this pool-based strategy is exactly this. So let's say that we have a little bit slow validator B, and we have validator A. We look from the perspective of node A. And let's say that this slow slow node just created its own chain of blocks and send it to A. When A just receive it, it looks fine. All this chain looks fine, so it's like satisfy all this like threshold, all this quorum based conditions of the DAG. It looks fine. And when node A creates its own new block, it references this block, the chain of blocks from guy B, and it disseminated broadcasts this block to other participants. And let's now look from the perspective of guy C. It just received a block from guy A, and since it doesn't have all this chain of blocks, it makes this block suspended. It knows that it references to something here in round 3, but it needs to request. It requested a block, and then it continues, and it takes time. And what happens in practice, I have some hidden slides here as well, is that this happens in practice quite often, even though nodes are not Byzantine by nature, but they Byzantine because of some problems, say in communication, in hardware, etc. That happens quite often. And we had, so you can see here, say suspended blocks. They could be really 100,000 suspended blocks that you need to keep also in RAM. And it leads to quite big problems, especially when we had crash nodes and we had such problems. And one needed just to fix it also in some just try to fix this gap in the protocol. So the goal of Starfish is just try to solve all the mentioned issues. So, and it's based on like these two ideas. The first one is decoupling the transaction data and the block header information. So the block header is basically consists of, say, hash pointers to the previous blocks, round number, the node, some signature, etc. Whereas transaction data is basically a set of transactions that is included in the block. And the block header also needs to contain some commitment to the transaction data. So, and the idea here is that since block headers are rather small, we can push them to the peers if they need them. But if we decouple the transaction data and block header information, then we need to add a new field, acknowledgements. Because if now validator nodes can send just block headers without transaction data, then some nodes might be not aware of transaction data. And you need to ensure that at least a quorum of nodes are aware of transaction data. So you need to add a new field for the transaction data, just to acknowledge that, okay, I have locally on my computer this transaction data from this, and this block. And now we need to rely on a quorum of acknowledgements to sequence the transaction data. And we can push block headers easily. And if we see that, okay, this transaction data should be sequenced, but I don't have it locally, then I need to pull it. Let me give you such an example. So what happens here? So it's very similar to what we had before. So here, in particular, let's say we have this leader block, H3. And similar, we try to understand whether we want to consider it as an anchor for slicing the DAG. And yes, again, here we have a quorum of votes and a quorum of certificates for this leader block. But now, let's look at the block D1, which is in the causal past of this leader block. You can see that in this block D1, we have some transactions, and let's say that it was created by honest node, it was sent to all other nodes, and they reference it. And since the whole transaction data was available to them, in the next blocks, they not only reference the block from D1, they also acknowledge, okay, I also know the transaction data of block D1, and all of they acknowledge this. And when we try to slice the DAG now, we need to find for which blocks we have a quorum of acknowledgement in the traversed sub-DAG. So here, for example, when we try to traverse starting from A3, we can find a quorum of acknowledgements for block D1 for transaction data. What means that transaction data D1 can be sequenced when we will consider A3 as an anchor for slicing the DAG. So as you can see, it just increases the latency by at least one more round because we need to wait until we gather a quorum of acknowledgements. Okay. So because previously, when we just sliced the DAG A3, now we also were able to sequence transaction data from block A2, B2, C2, but now it's not the case because we cannot get a quorum of acknowledgement for these blocks because there is basically no space between the leader block and these blocks. That's why we have a chance to sequence some transaction data only for blocks which are at least like 2 rounds from the leader block. Okay, it's good. So now with this decoupling, we can probably push the headers, the block headers, because when we construct the DAG, we rely on the information which is written in block headers, not on the transactions. And we can make a progress in the DAG construction, and there'll be no problem with that we observed previously. But again, from theoretical perspective, it's still possible to enforce some network conditions such that some transaction data will be sent between each pair of honest nodes. And for this reason, we just to amortize communication complexity, we suggest to use Ritz-Lemon codes. We consider them as erasure codes. What do we do here? So we just take the transaction data that is included, that's supposed to be included in the block. We divide it into shards. we encode shards with Rich-Solomon codes. So we take this f+1 shards and encode it into n shards. And if I'm a block creator, then I'm responsible for sending the whole transaction data of my block. But if I'm not a block creator and I'm responsible for sending only one encoded shard of the transaction data to others, together with a proof. So we need to make some commitment across all the shards such that we will be able to send our shard together with some proof, which can be verified against commitment included in the block header, which is signed. And now, if in all optimistic scenarios, you'll receive transaction data immediately from the block create, but in some pessimistic scenario, you will need to decode from f+1 shards, which were verified. Let me give you some detail a little bit here, but it's basically the repetition. So how block structure looks like. So we first take this transaction data, we divide it into shards, we encode it with these Rich-Solomon codes. We build Merkle root, for instance, over these encoded shards. And then the block header structure looks like this. So we have round, ancestors, acknowledgements, and also we need to include in the block header some commitment for transaction data. In this case, we just can include the Merkle root built on over encoded shards. So block header is signed, and then we send the full block. We send just a block, and block optionally could contains not only optional contains also transaction data or shard. So if I'm a block creator, then I send the whole transaction data and include it in the block. If I'm not a block creator and I'm responsible only for including my shard together with the proof, but I will do this only when the transaction data gets locally available to me. But so it's possible that I'll send only the block header if I don't have transaction data. But once I have it, then I need to send the one shard. Good. And with this design, you can see that, okay, I don't need to send the whole transaction data all the time. I do these shards, and in total, if you just look at from the perspective of one transaction data, then it's one sent completely by the block create. Also, there are n-1 shards that will be sent. Yeah, and if you compute the redundancy, so I can send up to 4x times more in total than the original transaction data, but this is not a quadratic. This is a constant factor in front of the overhead. Okay. And the broadcast rules then in Starfish is like that. So it's similar to Cordial Miners, but now instead of sending all the blocks, I need to send others block headers. If you think that they're not aware of the block headers, then I send it because the DAG is built on top of block headers. So we basically decouple these two data structures. In addition, we will send our encoded chart when the transaction data gets available to us. That's it. Basically, that's how broadcast is implemented in Starfish. Let's go to the comparison. It's a little bit more theoretical, and this concrete table is written under some very strong assumptions about how the DAG progresses, but it already allows you just to understand what this or this protocol can give you with respect to others. Okay, the last three protocols is basically the ones that we discussed right now. They don't require any reliable broadcast primitive, any explicit certificates, or no explicit certificates are attached to the blocks. They don't require any reliable broadcast communication. The above different versions of certified DAG-based certified protocols, they need some kind of reliable broadcast primitive. And yeah, this column is about block latency. So what time is needed just to understand the order of the block in the sequence of all the blocks in very positive scenario when everyone is honest. And the next one is like additional summon to the end-to-end latency, because as you can see, uncertified DAGs, they are built much faster than certified DAGs. And this additional summon is usually lower than in certified DAGs. And the next column is basically amortized communication complexity. And as I told, Starfish improves this communication complexity with respect to the prior work. Whereas for certified DAGs, there are some, say, communication complexity efficient reliable broadcast primitives that can be used to achieve the same linear communication complexity. Okay, let me just go a little bit more to the practice. So there are multiple ways, definitely, how you can broadcast the blocks. So in the vanilla Starfish, so as we just discussed, you need to push on your block. So all, not only block header, but the whole transaction data. But regarding the blocks of other validate nodes, then you need to push only block header together with one shard corresponding to your index. So we implemented also this variation of Starfish where you push only all your blocks, full blocks. But if I receive a block and I don't know some of the, say, parents, then I make a special request, missing history request. And upon reception such a request, you then need to push all the block headers with encoded shards. So it's a little bit different things, and it's kind of like gives different trade-offs regarding fault tolerance, latency. And another one that we also just discussed when thinking about production code, so maybe we will do this or this, and here you don't send the shards. The shards will be sent only if the transaction data is sequence, then you need to pull the shards from the peers. And in this, I have a few slides about performance evaluation. So this is a baseline scenario when everybody basically is honest. So here the networks are distributed over 10 regions. Globally, each transaction is of size half of kilobyte, and we use those machines. As you can see, when the load is not super high, and for instance, it's not too many validators, then Mysticeti gives really excellent results. Even it's below half of a second. For most typical blockchain regimes. But what's interesting that it's for very large for larger networks, when the incoming blocks could arrive in some unexpected order, Mysticeti performs versa, then this Starfish and Starfish variation called Starfish pool. This is quite interesting. And another thing that I want to point out is like these Cordial Miners, which also use a push-based dissemination strategy. You can see that the performance, there is a degradation in performance when we increase the number of validators. This is just because of the communication complexity. So basically here we have almost the slope just because we already occupy the whole bandwidth, because we push all the blocks in the previous round together with our own block, or almost all of them. And yeah, that's because of that, the latency just goes to infinity with not that much load. And we also discussed a little bit certified DAG-based consensus protocol, and the best available protocol that was which was publicly available and we were able to include in the simulation was Sailfish. And you can see that the latency is kind of like higher than in all uncertified DAGs, just because for constructing every new block, you need to build also a certificate for that. Because of that, the DAG itself, it grows slowly than in the approach of uncertified DAGs. But just a small comment that Sailfish, it has a separate also mempool layer called Narwhal, and because of that, the latency even worse than it could be. Yeah. And but okay, you can say, okay, this is just good scenarios, and for most practical cases, Mysticeti works very well. This is true, but when we have some kind of like attack scenarios, which we just discussed, when we have some missing chains of blocks and they are accidentally referenced by leader nodes, then the latency of Mysticeti increases significantly. So this is the case of 25 nodes with some reasonable load. And in the baseline scenario, so the bandwidth efficiency of Mysticeti is very good, or Starfish pool is good. In Starfish, as I said, the overhead could be up to factor 4. And in Cordial Miners, the overhead is approximately a factor of 25, because we have 25 nodes and you need to push quite many blocks as well. And but when we have attacks, for instance, I'll discuss them in a second. So chain bomb or equivocation chains bomb attack, then the latency of Mysticeti increases quite significantly. And in this case, it's a problem. So basically, when you are the unhappy case, there could be some problems with Mysticeti. As for Starfish pool, you can see that it's kind of, so Starfish is better than others in terms of like latency, but the bandwidth efficiency, just because you need to push shards all the time, so it increases here compared to this modification Starfish pool. Yeah, definitely compared to Mysticeti, because in Mysticeti you try to ask only what you really need. And as for these attacks, it's exactly what we just discussed, this chain bomb attack. When you just try to send a chain of blocks just before A becomes the leader. So in the next round, you know that A will be the leader, then you send your hidden chain of blocks to that guy, he will reference it, and it will send it to CND, and since they are not aware of this chain, they will spend time to download this chain, and they will not vote for this leader block in the next round, increasing the latency. And a cohesion chains bomb attack is very similar, but in the previous scenario, we did not make any equivocations. Here, just one guy creates many chains for all the nodes, and it disseminates its chains of blocks to just before the peer becomes the leader, it sent the design chain to that leader. And if it reference, then that leader will have problems because it will not get voting and certificates in time. And the same just for these chains of blocks, but maybe in around 6, 7, they will be revealed to the guys CND. Yeah, and under attacks, it's better to use this push-based strategy. Yeah, that's basically it for now. If you need materials, then I also have a slide in the beginning where you can scan and download all the papers and presentation.
Okay, great. Thank you for an exciting talk, Q&A time. Feel free to ask your questions, unmute yourself or type. Let me start. So yeah, I followed the link and presentation is also there, yeah? Is it true?
Yes.
Okay,
That's correct.
we will attach it to the post with recording and materials. Yeah, great. So let me start with few technical questions, tiny technical questions. So in comparison table, you have delta, but I think at the very beginning you called it sigma. Is it the same?
Let me just go here. No, it was, I mean, probably it's different fonts, but it was also small delta there. So basically there is a big delta
And small delta. Okay,
and
good.
small delta. Big delta is what we know that the network delay is upper bounded by this big delta, and small delta is unknown to us, but we know that the actual network delay is small delta. I mean, we don't know the delta, small delta itself, but it could be much smaller than big delta because like in some protocols, big delta is assumed to be say 1 second, but you still expect that maybe you run this protocol on well-connected network and it should progress much faster. Then you need to just rely on this unknown actual network delay delta. I mean, you want to derive some latency results in terms of small delta.
Okay, got it. Now a bigger question maybe. Could you please move to the first algorithm? So in general, optimistic looks like a kind of generalization or feature which is enabled to like traditional blockchains, making them DAGs and making them giving them some properties. For example, very first protocol is pretty similar to the traditional, let's say, PBFT, but we told that it is optimistic, so we do not just broadcast votes for blocks, but rather we enrich them with some new transactions, with our new information. So is this view available or like useful?
It's kind of that. So I mean, you're talking about Cordial Miners, right? The first protocol.
Yeah.
Yeah.
No,
Yeah.
but
So
they're about optimistic in general. Maybe we can see the correspondence between dark optimistic protocols and
yeah, I
already
can
existing.
explain a little bit just what's happening here. What we save here. So here we have like one signature, right? And it's the signature for the block. And at the same time, the same signature is used just for the voting for the leader. And the same for certificates. And here we kind of like, if we have a DAG-based protocol, then we will need to do this voting and certificates for every single block. We need to verify them. And here we kind of like save CPU work just to avoid this computations many times. But in general, yes, it can be seen as like a way to take some, say, classical BFT protocol and just to mimic similar ideas of votes, certificates, or directly on the DAG.
Okay, it may be useful not only for an analogy, but in general, are there any studies on formal verification for DAG-based protocols or not? Like, are they formally verified that, for example, this protocol or other protocols are correct, let's say?
Sure. Yeah, definitely. I mean, there are definitely formal proofs why they will lead to the just consistent sequence of, say, blocks or transactions. Definitely.
I mean, not just mathematical proofs,
Ah,
human-based, but
ah,
with formal languages, with formal models.
you mean for specific implementation? So what?
Yeah. Well, and not maybe implementation. With implementation, it is more difficult, but with protocol itself. So formal specification and formal verification.
Okay. I'm not aware actually.
ELA plus.
Yeah, I'm not aware of formal verifications of, say, pseudocode. Yeah, I'm not aware of this.
Okay, so maybe it is an interesting direction, and from theoretical point of view, maybe we can derive these proofs based on existing proofs for standard blockchain protocols. So we already have a lot of formal verifications for classic blockchains, and if we have such an analogy, it may be useful in proof. So maybe we can somehow transfer proofs from
Yeah,
one to another.
might be. Yeah, might be, but I'm not aware personally about this.
Okay, got it. What else? About communication complexity. If we again refer to classics, then in Bitcoin we do not broadcast any uh, uh, big information through the network, but rather we broadcast. They use very engineering solution. They broadcast inventory messages, and if you look on network statistics for like real nodes of Bitcoin blockchain, they really send quite a lot of inventory messages where they just list what do they have, but they do not broadcast these blocks, these transactions, but rather they inform their peers that they have these guys, and only upon request they send these.
Yeah, but it's indeed like rather engineering solution. So the goal here was just to say kind of like prove things that they will work as expected under, say, strict model, and that the latency for every correct node will be bounded by, say, given value.
Yeah, but okay, so it is not for proofs, not for asymptotics, but what about such engineering modification? Have you seen it in any protocol? Would
No,
it be
I
useful?
mean, as I said, it's already, they have this, first of all, just, I mean, it's kind of like, there are some, so as you said, that nodes share with their peers what they know about others. And now for Mysticeti specifically, the, they design specifically some such heuristic one more layer sub-protocol where they exchange what they know, such that they will not meet the situation when you just have a chain of blocks which is not well disseminated. Yeah, probably should stop creating your new blocks. I mean, there are such like engineering tricks to improve, say, stability, but uh, not so many. Yeah, I would say.
Yeah, but okay, so for this Mysticeti protocol, we see that they utilized bandwidth very good, so around 1. But yeah, but they have very specific structure for that, and we can't generalize this structure at least easily
I
for, let's say,
can maybe
Starfish.
a little bit explain why they use this pool-based strategy, because they started the path, just the developers of Mysticeti, they started their path with certified DAG-based consensus protocols. And they just, even in the paper, they said, okay, implementing push-based strategy could be complicated just because of this quadratic complexity. That's why we are going to use pool-based strategy. And they had a series of certified DAG-based protocol, and pool-based strategy was excellent because you cannot create a new block if you don't have a certificate for your previous block. And certificate means that you already well disseminated your block to all others. So basically, this certified approach just cuts this problem from the start. So you cannot create a new block if you didn't disseminate well your previous block.
They are optimistic, but very
But then,
limited in their optimism.
yeah, but then they extend this pool-based strategy, dissemination strategy for optimistic or uncertified DAGs, and apparently for real deployment, not only on test beds, it can come to some problems, big problems.
Yeah,
But
thank you.
I mean, they can be fixed by some heuristics. But
Okay, it seems that Yash had a question, or it was just misclick. Okay, if you have. Okay. Okay, what else? So yeah, around our seminar, we have quite strong group about formal verification from Moscow State University, and maybe it may be interesting to bring formal verification to this area as well. So does it sound potentially interesting, or you more focused on like applied protocols and less about the theoretical properties?
I
What do you
mean,
think?
I'm curious about theoretical process. Again, like I'm interested in just say bounding the latencies for many protocols, and apparently not so many rigorous bounds in the space here. So because people, so for instance, the table that I presented, it's not rigorous. It's under very strict assumptions that are not even realistic. And I'm curious, say, in deriving explicit bounds for the latency. So I'm curious about, say, what we can do, say, from the say mass perspective. Yeah, and this
No,
formal.
it's just about logic that your protocol, it's not about theoretical bounds, it's more about that your protocol works as you expect. You do not miss any like vulnerability in terms of logic
Yeah,
inside your protocol.
yeah. I
Okay,
mean,
okay, we can
that
discuss
would be also interesting. Yeah.
yeah, we can discuss it later. And also in numerical experiments, you had sailfish, I think, or something like that. But in table, you had version 1 and version 2 of that protocol.
Yeah,
So
but
which one was publicly available, version 1 or version 2 or some other?
no, none of them, because in the table it's just pure, say, theoretical protocol, whereas in implementation it's a protocol built on top of prior works of Bullshark, and Bullshark was built using some additional layer mempool dissemination called Narwhal, and where just every node has a special worker, and workers, they exchange transactions with other workers, and transactions should be, or batches of transactions should be also certified. And then when you create a block, you need to include certified batches of transactions in the block. So it's a special implementation, I would say. It's not 1 and 2. And if you would have selfish 1 or 2, then the latency will be smaller than was shown, but no such implementation is available. Yeah.
Okay, got it. Maybe two more questions from my side about the topic itself, and then a few questions about organization. So yeah, first, technical question is about your last algorithm, Starfish, and about redundancy. So could you please again summarize in a few sentences what was the gain of redundancy, or just correct me if I'm understanding right or not? So you introduce some redundancy in bandwidth, and at the cost of this redundancy, you send only pieces of information, let's say transactions. But good news for you is that once you receive enough information to reconstruct this piece of data, let's say transaction, you are done, so you received it. So at the cost of this redundancy, you just get so you introduce some redundancy, but as a result, you save some bandwidth.
Yeah, I save some bandwidth in the worst case when the node will not disseminate the transaction data to everyone. But if it will send this transaction data, say, only to the third of all other nodes, then others will not be aware and they will start requesting. And if they request from this sort of nodes that they have transaction data at the same time, all of them will send this transaction data to those nodes, and it will lead to a big communication complexity for this transaction data. So what we did instead is basically, just encode transactions. We add some redundancy, definitely. Then the block creator, it sends the full transaction data to everyone, and all others will just send only pieces from this encoded transaction data, only some pieces, such that in the worst case, in total, the maximum information that can be sent is 4 times larger than the original information. But if you receive a sufficient number of pieces, then you will be able to reconstruct the original transaction data. So it means that if the node is honest, then you will receive the transaction data from the honest node. But if the node is not honest, then you will reconstruct the transaction data if there is a quorum of other nodes who has this transaction data available. You will receive pieces from these guys who acknowledged that they have transaction data. You receive pieces, the corresponding pieces, and you will be able to reconstruct the original transaction data. So it's basically to attack this scenario when dishonest node reveal its information to only few peers.
Got it. Thank you for the clarification. And back to multiple leaders and intersecting waves. So in your hypothetical example, we see only 4 nodes, but any like results or estimates, so how many leaders we should select, and how should our waves intersect?
Yeah, sure. I can say. So in Starfish, we use leaders every round. So it's like pure pipeline. Yeah, we use something like that. But what was done in practice, so they tried different number of leaders per round. But apparently, as I said, so for instance, in this scenario one we just discussed, you cannot continue the sequence of committed blocks if you have some blocks in pending state. And when you have very diverse, say, network, then some validators, they are slower than others, and you will be slow down your, say, committing leader blocks will slow down by committing slow nodes, just because you need to process blocks in this sequence. That's why even in the paper it's written that by experiments we use at most 2 leaders per round. Even for large scale network, like say 50 nodes, they didn't recommend to use more than 2 leaders. But in the production code, they use just 1 leader, and we also use 1 leader because multiple leaders also lead to some other complications. Because as I just said, there could be, say, slow validators, slow nodes in certain sense. For instance, they located somewhere, say, in Australia, and they're not well connected to the rest of the network. And in principle, what we can do just to improve again the latency, get some gains in terms of latency, we can say, okay, maybe we should not assign slow validators, slow nodes as leaders. Maybe we should only include nodes that are very well connected, that are not currently crashed. And they propose to do such a modification such that they have a schedule for leader nodes that is updated every, say, 1 minute. The schedule of leaders is updated depending on the results in the previous 30 seconds.
Okay, and what about waves? We've seen non-intersecting waves and new wave each round. Any intermediate possibilities may it be
Yeah, there
beneficial?
could be, but as I said, it can be. I'm not sure. I mean, it's possible to generalize, but I'm not sure about the gains in terms of whatever else here. So, for instance, first we have pipeline, then there is some gap between waves, and then again, it's mostly could make sense if like probably some leader is a little bit slower. Maybe it's just can be fixable by some other mechanism that exists, like changing the order of leaders.
Okay, maybe we can have some adaptive mechanism for some regime of network. It is good to like start waves each and every round. Sometimes it is better to have non-intersecting.
Yeah, probably. Yeah. I mean,
But
even
no
just
adaptive designs for now, yeah, in this
yeah,
sense.
I am not aware. I mean, there is only adaptive in terms of who is going to be the leader.
Okay, got it.
There
Yeah, I
is
lied about last question about material. I have one more. Any research about MEF around it? Because it seems that each and every algorithm you've presented today, well, discussed and presented today, is vulnerable to MEF attacks.
yeah, but I mean, it's kind of like a little bit complicated topic in the sense that okay, we just have this sequence of blocks. Okay, good, but then the transactions are not usually extracted in the sequence of blocks. So there is some special sorting according to, I don't know, gas or some hotness of the objects consumed by transactions. And then it's getting very messy how to just do this MEP. But
Any practical
there
any
are some
method
models,
in
yeah,
IoT?
where MEP just is just discussed, but with some simplifications. And there are some practical, like for instance, Shio suggested just to explore this MEP world to everyone and create so-called sort bundles of transactions such that you can extract value not only validators, because currently the network that is used here, it's basically hidden, so nobody knows what happens in the network. So blocks are created by, say, consensus nodes, consensus validators, but the rest of the network is aware only of, say, commits that are or the slices of the DAG, or just only of transactions there, or some checkpoints, and only, say, consensus nodes can play with MEV. but yeah, there are some plans how just to stream these consensus blocks and to make this information more publicly available. But there are a few papers about this MEV, and yeah, we are also looking. Actually, we have a group of people just looking at MEV on DAG-based consensus protocols.
Nice, very interesting. Few organization questions. So you are from IOTA. Are you or your organization open for collaborations with researchers? Are you hiring talented researchers or students? Do you have maybe some grant programs for individual researchers, developers, or groups?
Yeah, that's what I cannot say because I'm not much aware of it. Probably there are some possibilities that should be aware, but is
All
what
questions.
I can say. Yeah, probably it will be rather short grants. Yeah,
Okay, it's about grants. Okay. What
most.
about other questions? Are you hiring students, researchers?
We are not actively. I mean, currently, for instance, in our group, we have one position where we just hire, say, but we hire a little bit more engineering guy, not say researcher. So because yeah, most of the like research should be anyway kind of like applied to practice, and yeah, currently we have no opening.
Okay, and
Position.
engineers, more engineering, more developers.
It's
Are they
called
for
like
input
consensus
output?
engineer. It's called like consensus engineer or senior consensus engineer.
Okay, got it. And what about collaborations? So you are open for collaborations somehow. Is it
Yeah,
true?
we are open to collaborations. Probably also even within this consensus topic, we can say find some say subtasks that can be done, which can result to really good papers, and maybe it can be also just go to the production. Because especially just for students, if you don't have much experience even in programming or all these things, you can just dive into say code base and contribute not only say in practice, but also you can contribute say from theoretical perspective. So
Okay, great. We have such people around the seminar, so
yeah,
maybe
especially if they have
will
say Rust
contact. They
knowledge.
can contact you. Yeah, is it true or
Yeah,
better?
this is completely true. So for instance, for consensus, I have say a list of topics that can be explored. And I think it will be beneficial for both sides just to do some kind of like applied research, which can.
Nice, great. Last chance to ask your questions, Igor. No questions. Okay, it seems that no more questions. Thanks a lot for an exciting talk and all the best in your research. Bye.
Yeah, thank you. Bye bye.